So I've been thinking about this quote a lot recently. No man ever steps into the same river twice, for it is not the same river and he is not the same man. Anyway, what we're going to look at today is position, velocity, and acceleration. I actually just think I'll let the video play for the first minute and then I'll go back and I'll explain it again. Probably not very well, but I'll do my best. So just have a look at this video and see if you can make some sense of it as it moves through. So the first thing is position. Consider some point P moving on a number line. And then what we might want to do is talk about velocity after that. And that's how fast the position changes and in which direction. And then acceleration. So acceleration is then a change in your velocity over time. It also has a direction as well. All right, so hopefully that maybe made some sense initially, but what I'll do now is I'll just go through and explain it. I'll put timestamps on the video to explain position, velocity, and acceleration, because this is going to be useful for your study of kinematics. It's sort of an introduction, and I think if you get these concepts down early, it's going to make things a lot easier for you. So yeah, if we start here, so position describes where something is measured relative to an origin. So throughout all of this explanation, just remember that the thing that we're actually analyzing the motion of is this point P, and that's not going to change throughout the whole thing. That P is just going to move up and back. So we've obviously got our origin here at this point here, and this point P, the motion of it is just going to go up to here and it's going to come back. And then so if we were to think of that as a function, I think you'd actually agree you'd end up with a sine function. If it starts at the origin, which we have sort of starting here, if it moves up to +3 and then it comes back to the origin and then down to -3, back to the origin, and it just repeats that back and forth, then you're going to end up with a function x of t which describes the motion of this point P from the origin, and it would be equal to 3 sine t. And so I think that's probably the most straightforward part. Just be mindful that you can have negative position values, right? Because you can be, if we define to the right as being positive, then -3 would be being to the left. So that would be down here, right? So yeah, all of these quantities that we're going to be talking about can have positive and negative values. And what we'll talk about next is the velocity. So if we return P back to that point, velocity is basically this idea of describing how fast the position changes and in which direction. So that's basically the derivative, and if you've come this far in maths, then you know that's sort of associated with the derivative. So we're talking about the rate of change of the position. And so if we think about this graph here, if we were to sketch the velocity graph, it's going to look something like this. And let's just play it out. So if we were to play this out, we know that the derivative of 3 sine of t is 3 cos of t. So we're going to call that x dash of t, or we can call it v of t, because the velocity is a function of time now, and we get 3 cos t. And so if we play that from the start, we can start to get a feel that, let's pick a point. Let's pick this point here when p is right at that point 3. It sort of makes sense that the velocity is 0 at that point, because the velocity is not changing at that point. As it gets to that point P, you can see that it has to slow down. As it moves to that point, P moves there, it has to slow down, and then it has to reverse. So the velocity is 0 at that point. So you can start to see why those points, let me get it right, those points match up. And then you play through, right? As P moves to the left, we get a velocity being -3. And that should make sense. It's moving to the left. So if we just play that, if we just let that play a little bit, it's moving to the left. And then P, when it starts to move to the right, the velocity becomes positive again. Okay, and then you just get this nice sort of pattern going on. So that's basically, yeah, hopefully you can see how that green function now is describing the motion of that point P as it moves along, okay? And then, so the next part is obviously acceleration, which is going to be the second derivative of position, or another way to think about it is it's the rate of change of velocity. So acceleration describes how velocity changes over time, and it looks like this. And if we just put the rule in there, the rule is x double dash of t, we can call that a of t is -3 sine t. And let's just play this again, so you can see and start to piece together, see if you can come up with an explanation in your head for why this point R shows the size of the acceleration. So let's go back and let's sort of analyze it as we go. Let's go back to the start of this. So let's go here. Okay, so let's think. P at the very start, if we're just looking at this, it's moving towards the right. Let's pick this point here and let's see if we can explain. All right, this is where it gets tricky. So this point P, again, is at its maximum it's going to get to the right. And then you can see that the acceleration is actually -3 at that point. Now, you're probably wondering, why is the acceleration negative at that point? Well, think about it like this. That point P is, think of it like an elastic band from the origin. As that point P gets to that maximum of 3, that's when it's being accelerated most back to the left. So you can sort of think about it as the rubber band stretches as it goes from the origin to that point P. The force, if we think about it in physics terms, the force is increasing on that point P because it wants to be pulled back in the other direction. So remember that this negative, when the acceleration is negative, it doesn't mean deceleration, it means acceleration with the direction. So this point P at this point is being pulled back with the most force to the left at that point. And then as we play through, at this point here, this is where it's interesting, the point P and the point R are obviously at the same point, 0, and that makes sense because at that point, it's traveling at constant speed. So let me just show you that. Watch this point P as it moves past the origin. That's when it's actually traveling at constant speed. And then it has to decelerate to 0. And so again, at this point, the acceleration now, the elastic band's pulling the other way. The force wants to pull it back towards the center. So the acceleration is positive, which means the acceleration is a vector. Remember, it's pulling it to the right. So it wants to move it to the right. And so the acceleration is large. And then, yeah, you get this situation. I think a common misconception is that when you have negative acceleration, that means deceleration, but it's not necessarily the case. You need to consider the direction in which that point P is traveling. So maybe just one more time for good measure so you can see. So there you go. Hopefully that made a bit of sense. I ran the risk of confusing people a little bit, I think, by sort of putting these points R and Q on here. But remember, P is the thing that's actually moving. These R and Q points are just showing the size of, or just showing, the size and direction of the relative quantities, whether they be velocity for Q or acceleration for R. Anyway, hopefully you pieced that together a little bit in your mind and it made some sense. If you did find it helpful, give us a thumbs up. Let us know what else I can help with. Good luck with all your studies, and I'll talk to you soon.